Today's lecture is going to be about autoencoder. I also hope to use autoencoder as an example to go through backpropagation and gradient descent. Okay, all right. So let's start with those two terms, encoder and decoder. This is a very simple network of 2, 1, 2 and multi-layer perceptron. We have 3 layers: input, hidden, and the output layer. On the left-hand side is the equivalent matrix multiplication format, and also on the right-hand side is the graphical representation that's more common in deep learning text. Okay, so let's analyze this network just a little bit. We're going to focus on the number of dimensions. So this is where the input is. We have 2 dimensions, 3 different inputs. So across the horizontal in this matrix representation is batch, and across the vertical dimension is features. In the graphical form, that orientation is transpose, and so that the vertical is for batch and also the horizontal is for features. So I have 2 features per example, 3 examples and 2 features per example. Okay. And then in the internal node, you will see here that we have only just 1 node, meaning that the dimensionality of the feature in the hidden layer is just 1. So 1, and I'm going to just quickly draw like this, 1 for 3 data points and 1 dimension each. So one way we could draw the mapping is that we could draw like this from 2. I have 2 here and 1 down here. And so we can draw this triangle. You see this triangle whenever you see an encoder. And then this triangle going from large to small in terms of dimensionality is what the encoder typically looks like. So I'll write encoder over here. So this is 1 encoder. And then we have input feature up here. And then the output of this encoder is code. And sometimes we look at the structure because it looks really narrow here. And we usually refer to it as a bottleneck. So I write bottleneck over here. Okay. And then on the going to the left on the matrix side, so we could draw something similar. So we're going from 2 dimensions to 1 dimension. So this is a bit more distorted triangle. Hopefully, I also trying to hit some of the weights over here. Okay. All right. So this is what it looks like. And we would like is to expand in dimension to on the lower end, we'll go from 1 to 2. So 2 to 2 to 2. Again, a batch of 3 data points. And so we're gonna go back up here. So this block, we usually call it decoder, that will like to take the code and trying to decode what's in the code back to some kind of signal. So this output signal here. Okay, so input, encode, and output. And here we can just repeat this while we're writing here, input, encode, and output. Okay. All right. So I would like to hide the link a little bit. So just like to tell you a little bit the pattern of the signal here. If we look at the signal very carefully, let's erase this. You can actually see the signal. 4, 4, 3, 3, 2, 2. What does it tell you? There's I'm telling you that it's kind of hidden code between each of those 3 input. So you might see some redundancy, right? 4 repeats again, 3 repeats again, 2 repeats again. So when I ask you how many dimensions do I need to actually represent the signal, it's actually just 1 because it repeats itself. So if I will write okay, I don't want to erase this code. I would like to extract that hidden code by hand. So one thing I can do is that maybe I can use weight 1, 0, and bias 1. They'll be able to get 4, 3, 2 through maximum application. If you don't remember what I'm talking about, you could refer to a previous lecture. So this is a way I could do 4 times 1, 4 times 0, and 1 times 1 to be biased. Actually, I don't want to add any bias. So the bias is actually at 0. So end up getting 4, 3, 2. So I kind of do it by hand. If I would just write a very simple encoder here, turns out, so this set of weight is a very, very simple encoder. to encode my input from 2 dimension to 1 dimension, just to capture only just 1, 4, 3, 2. So this I'm doing it by hand. If we would like to ask the neural network to learn those weights on its own, for machine to learn it, we need to kind of provide some kind of training examples here. We'd like to be able to say, well, what would be how can we actually instruct this network to learn this set of weight 100 instead of I just hard code it? And one way is that to use those code and to feed to another layer of the network, in this case, my output, my decoder stack here. I have this two set of new weight. If I am able to use the code to reconstruct or recreate my input, so basically my output is my input. My output is an input. So my output is my reconstructed input. So the logic is that if the code is able to capture what is really inside a signal, we should be able to use the code to completely reconstruct the input. So this is the idea. So if I would write the weight myself, I want 432 become 443322. And this is actually a trivial example. So I just use weight is 1 and bias is 0. So I'll be able to get 432 and 432 and out of this network. If I will code this, I will use 100, and this will be my make-tree modification. So I'm just implementing this very simple encoder and through match modification. And if I then I implemented the very simple decoder also through metric modification, except that before I do that, maybe I should actually enter those weights and biases over here. And now we're going to do metric modification, take my weights over here, and take the code with the augmentation of ones in order to calculate biases. Okay, and so if I will hide my ink, and then we see that this is a clean version of the encoder decoder architecture. And you can see that the output and the input, they look exactly the same. Okay, so let's bring the ink back. That's why we use this word called auto. So auto means just kind of self, means like kind of same. So when auto is the idea that scroll down a little bit, my input and output, we want them to be the same. That's why we use this particular encoder and decoder architecture. That is, we usually call auto-encoder. Let me just write down here. So this is the decoder weights down here, and up here is the encoder weights. So when we talk about auto-encoder, we're referring to this thing. This thing, okay? So let's draw this again from 2, getting messy a little bit, but I hope you can bear with it. Let's erase this 3. Just 2, 2, 1. And this is equivalent to this triangle to the right. And that's my autoencoder. And decoder, why do we have decoder there? I realized I forgot to add R here. So decoder is this technique that allows us to train the encoder. So I would like this set of weight eventually to get my input back. That's reconstruct input. So this is ideal output. So we have 1 0 1 0, get 4 4 3 2 2 back. But then in reality, before it learned it, maybe the weight's more like what happened here? 0.9, right? So say before they actually learned, you can see that 0.9 is not as ideal, because instead of getting 4, 4, we get 3.6 and 4. It's about 0.4 away from an ideal value, which is 4 for this particular number. And for 2.7, it's about 0.3 away from 3. 3 is my target because I want to be able to reconstruct my input signal to do exactly the same as the input signal. So eventually, we like to have a mechanism that they will just update this way, say 0.091, and kind of getting closer, 0.92. Eventually, we'll get to 1. And then here, the input and output are exactly the same. We would like to be able to say, hey, the loss of this training has become the smallest, which is 0. There's no difference between the two. Okay, so this is like a high level logic of the auto-encoder architecture that is usually has this encoder and decoder form. So we have this two triangles kind of in this way from big to small, bottleneck to big. So that is and this we can draw this way, 1 to 2 architecture. So the first one looks a bit messy. I have another example just to highlight some of the points we're talking about. So I would like to draw first the encoder. So for over here is 2 to 1 encoder. Okay, so this is my encoder. And then equivalent drawing on the left in the metric form is kind of look like this. There's a bit distorted triangle shape. And on my decoder stack, they will be going from 1 to 2. Look at this triangle, but in a different orientation, flipped upside down. And for on the left-hand side, I can draw the same thing to allow you to. So this is drawing to help you build the intuition of what the encoder and decoder does. And let's write mathematics in this example. So I would like to have my input X and my hidden state H and my output Y. So I would like to have encoder function E, and then it takes X as the input, and it's going to get H, a hidden state, which is lower in dimension, maybe 1. That is my code. H is my code. And I like to take this code, use decoder. If my code is the right code, I should be able to take my code and feed it to a decoder. I'll be able to get a signal. And this signal is actually, I like it to be X. And this is the auto part of the auto-encoder. Why? My reconstruction signal is the same as my signal. Okay, and then we will write the objective function for it. We want this to be minimized, the distance between X, my input, Y, my reconstruct signal, to be very small. And then eventually it should be reached to 0 when they are identical. So that is mathematical interpretation of this. And let's look at the number 574624. If I will ask you to see this as a puzzle, do you see the underlying code of this signal? If you are telling me that, well, the signal is actually, this seems to be a 6, somewhere in between the midpoint between 5 and 7, and just one apart from each side of 6. And this will be 5. This will be 3. So this seems to be like code that could have generated this input signals. That use a different color, so it's more distinguishable. So my code is going to 6, 5, 3, and now suppose the machine trying to learn this, what will be the encoder for me to produce 653? So maybe it will be something like 0 0.7. Sorry, let me just say 0 0.7, 0 0.3, and maybe no bias. And what will be, how do I know whether it's good? Maybe I can use some kind of decoder 0 0.7 and 0 0.8. I have some kind of random initialization for this weight. And then, is it good? Is it good? I don't know. So they just implement this for now. 0 0.7 and 0 0.3 and 0. And I'm going to do multiplication to implement this very simple encoder. I select 2 matrices, including this extra rows of 1 for biases. And I implemented my encoder. Again, very simple. In this case, it is a matrix multiplication. Actually, no, here. So one matrix and another matrix, okay? But I didn't put the weight in yet. So I put the 0, 7 and 0 and 0 0.8 and 0. Can you see this number? Let's hide the ink a little bit. Are they good? Not that good, right? They're still 3.92 and 4.48. That's still quite, there's some distance between the two. So what I would like to say, maybe I could eventually add a little bit more weight and getting closer. Okay, the first row seems to like looking promising, becoming more like 542. Okay, in my second row, if I add more weight, maybe I decrease the weight, feel like, oh, actually getting further away. Maybe it's not that great. Maybe like this is better, okay? And if I add more biases, maybe get even closer. Eventually add to 1, get it maybe even better. But then if I change this thing, so am I making my output better or not? But in fact, the real answer is 0 0.5, 0 0.5, because then it will take an average between the two numbers. 5, 7 becomes 6. And then the real answer is 1 and 1. and then we have a bias of -1 over here and 1 over here. And if that is a perfect result, and then because I know it's a simple example, I can solve it with my hand. But in this case, a machine will use this process called back-propagation and gradient descent to just keep upping the weight. And then we have this target or objective we want to reach. In this case, in the auto-encoder case, just basically reconstruct yourself, the auto, where the auto comes in. All right. So it is there's a very useful architecture auto-encoder with this encoder decoder stack. We'll see that very often, quite a few times, even all the way to transformer diffusion model. This all have this idea of a heavy encoder and decoder putting together. Your goal is to train the encoder, but you use decoder to tell you how close you are to be able to reconstruct your signal. Again, one more time, I think it's important to emphasize. Your goal usually not to get a decoder. Your goal is to get the encoder, and then use decoder to tell you how good you are. But then when we get further along, eventually you would like to generate new sentences like in transformer. So decoder and encoder together is actually a goal. So I'm kind of complicating the situation in my explanation, but let's just focus on encoder and decoder and autoencoder. And with this respect, in this context of autoencoder, our eventual objective is to get my encoder. But we use decoder as a kind of oracle or like so things that can provide you feedback, how close you are to get your perfect encoder that can capture the underlying inherent secret code of your signal. Okay. And they tend to be a lot lower in dimension. So let's look at a more practical case of a larger encoder decoder architecture. So in this case, we have 4 nodes here, 4 nodes, 4 and 2. Use this color, 4 to 2, and then eventually to 4. So it's like higher in terms of dimension. So if we draw this, so my encoder stack could look like this, and my decoder is going to look like, let's maybe use oranges here. So is decoder here, okay? And then quickly implement this, and there's going to be mainstream application. Again, this is a review of the multi-layer perceptron stack. And the redo function, I can use my map and take every single element from before. I use a lambda function and to take each element x, but I apply max and x and 0. So they're very typical ReLU input ReLU implementation. And then you see no effect because ReLU have effect only if it has some negative value. So if I change the biases lower, eventually we have some, this is not as interesting. Maybe this is interesting. So then you can see that this 1 becomes 0. That's what ReLU does. And then eventually I'm implementing my decoder stack, which is only 1 layer. So it can be implemented with a maximum application again. All right. And so this is my code. So this is my code. This is a code. Okay. And then this is signal. So they have signal here, code, and output. Now, okay, so this is a slightly bigger example from before that with more dimension, 4 to 2 to 4. Let's look at an even larger example with multiple layers. That's just not just 1 layer for encoder decoder, but multiple layers. So we can take a quick look. 6. So it's 6, 4, 2, 4, 6. Okay. And then let's just implement the last layer with maximum application. So this is a 4 to 6 transformation, linear transformation. And then I just again simulate maximum application and get my output. So first question is, where do you see the code? So code usually at where the bottleneck is, so we have this 2. This is my code. And with a maybe let's say this after the ReLU activation function, which is the output of this node. And so this is my code. So just say this is my code. And let's zoom out a little bit so we can see everything together. So let's say 75%. Now I'll be able to, guys, just move out a little bit. So see the whole thing. And now we'll draw my encoder. So can I draw encoder? let's use orange to draw my encoder. So this is an encoder. So this is my encoder. Okay, and then we have down here. So this will be my decoder. And you can see the equivalent magnitude representation to the left. So this is my decoder. Okay, decoder, right? So encoder, decoder. Okay, so what I just did is I show you two different ways that we could scale this. We started with this trivial example of 2, 1, 2 encoder, decoder. You might have your question in your mind that why do I care about this such a trivial example? It's a total example. It's never gonna be practical. So in one way is that we could simply increase the number of nodes each layer. Also, we could increase the number of layer in this direction as well. And so that's how you could scale this encoder decoder to be much larger, but they still follow the same principle that we discussed today. Okay. Next, I would like to discuss the loss function. Earlier on, I mentioned that we like the decoder to provide some feedback how well we are doing in terms of being able to reconstruct the signal from the code. And then also means that how good the code really is. And that is where the loss function comes in. We can use this, actually calculate this, how close we are to the original signal. So let's zoom out zoom in a little bit back to 100%. So this is our example L2 loss section. So this is the structure we looked at before. Kind of going back to a simpler structure, it's easier to explain this concept from this point on, loss function. And then next we're going to talk about gradient, and next we'll talk about backpropagation, and next we're going to talk about gradient descent. I'll use this a slightly simpler architecture here. So we have 4, 2 with ReLU and 4. This is my architecture. And then, so now to focus on the end. So this is my output here. Okay. How good is this output? We'll want to say, oh, the target. What is the target? The target is actually, I would like to use Y with this symbol to denote the target. It turns out for my autoencoder case, I like this to be X. That's why I have this box over here. So this X is, how do we get X? We'll just go back, equal here and go back up here to select my input here. So this is how I implement the target here. And so now you can see here, it is not exactly the supervised training because I'm not really specifying the label. I'm not telling the network, oh, it's a dog, it's a cat, it's a car, it is a face. No, when I'm not teaching them, I just ask the network to look at yourself. Look at yourself. The people like semi-supervised, the network using itself we actually call it the semi-supervised training. In fact, that the supervision comes from itself. There's still supervision because you have target, but it's not entirely manual. Human is not providing the labels. Humans, we're only telling the network, look at yourself for the labels. And so this is the labels. And then for L2 loss, then is the equation for L2 loss is going to be, I want Y and minus my target, and then take a square of it. And in this case, because my target is actually X, okay, in this case. So this is my L2 loss. Let's say, right, bigger L2 loss. But very often we add another scaling factor of half, dividing by half to this definition. And the reason is, you'll become very clear in the next section. The reason is that we add this half, we're going to simplify something. What does it simplify? Simplify the gradient calculation. You'll see in the next section very quickly, but just put it up there. So when you're trying to define this objective function, if you scale it, it's still going the same direction. All we care is about, are we going to the right direction to reduce your loss? Loss is a bad thing when to reduce it, so it's minimal. Similarity is a good thing when to increase it. So earlier on in the compare lecture, we spent a lot of time talking about the difference between distance and similarity. And so loss is more like distance. We would like to minimize in order to get better. And eventually we get a total loss. How do we do it? We just take a double summation over this term. Why? Because 2 dimension. One is over batch. The other one is over feature. If you can see in this way. Okay, going up a little bit, you can so this is feature dimensions, 4 different feature dimension, and this is batch. Okay, so I use this example to show you how to calculate batch at a time. All right, let's implement this. How do I implement this? It's going to be, let's say 1 over 2 times, and y, where's my y? Y is here, just select my y here, actually here, select my y, and minus x, select my x, okay? But I would like to actually put my parentheses here in order to take a square of this term. So this is going to be my L2 loss and individual. It's for individual feature for individual batch. And total loss is a summation of this. And there's a double summation over this matrix, but Excel, you use sum just like do this. So 83 is a total loss for this one. So if you would say, hey, if I'm going to add this 0.1 from 0 to 0.1, is loss going to be increase or decrease? I don't know. Let's just experiment. Say 0.1, add a little bit more weight, okay? And then, so it goes up. The loss goes up from 83 to 84. Do you see that? Okay, so we have loss over here, and then we have weight over here. So what does it tell you? What it tells me is that, so the partial derivative of loss with respect to x is positive. Do you see this? Because I add a little bit weight, but loss goes up. Let's just try this one for this location. What if I add a little bit weight over here? It goes up, so it's right direction. Okay, let's find something that's actually opposite. Maybe here is minus 10. So minus 1, if I add a little bit weight, it means it's going to be 0.999. Okay. Does the weight go down a little bit? Maybe it does. Maybe just say 0.9. Go, actually, sorry, too much. 0.1, I'm going to become 0.9. So it goes down in this case. So for this particular weight, the partial derivative of loss with respect to this weight is actually less than 0. Okay, so meaning that if you increase the weight from minus 0.9 to minus 1 to minus 0.9 is increasing. And then the gradient is actually in the opposite direction. So this is experimentation for you to kind of get a slightly different idea of what gradient is. So how do we actually calculate gradient is in the next section. So let's talk about it. How do we calculate this gradient mathematically? So in calculus, to calculate the gradient, so we'll take a derivative of my loss over this y. What is y? Y is here. So the last thing, the output of this is y. So use y here. So over y, what is this? And it's going to be, can you see this clearly? Okay, let me scroll down a little bit. You can see it. Okay, better. So what is L? L earlier, we define it as we add this extra 1 over 2 and y over minus this target y square, and the denominator is still the same, okay? And this is where your first year calculus comes back, hopefully, to your memory. So there's going to be half and 2 to the front. So not here. 2 will just kind of move out to the over here, right? 2 and then becoming y minus y. And then there's going to be another 1, but then this is going to cancel out. Eventually, you become this very simple. Wow, this is where the magic comes in. It turns out the gradient for your final output of your network, if you use L2 loss, is just simply going to be your prediction, which is y, minus your target y. Okay, and then how to implement this? So it's very easy. So it's going to be equal. I'm going to select my y. Let's go up a little bit. You don't have to go too far. Select my y over here, and minus. I type minus. Select the target. What is target? It turns out target is x because we are talking about autoencoder. Okay, that's it. All right. Now this is as easy as you can see that it turns out to start your back propagation to compute the loss gradient, the equation is reduced to the simple form of taking the difference. between your prediction and target. And in later on, we're gonna see this format many times that when we use softmax, when we use sigmoid function, and with some kind of interesting mathematics, it always turns out to be the very simple form of gradient, something minus something. That is how the gradient term simplifies too. That's very easy to code. And then everything else is just follows. And then, okay. Anyway, now we're going to get to a really seemingly tough topic called backpropagation. So today my goal is to help you build intuition that, well, backpropagation, if you put it out in this metric format, it's really not super hard. But if you see them in this just symbols with tons of these things called Jacobian matrices, it just can get lost very quickly. But since this class is more computer vision, so I'm just going to give you a feel of backpropagation can be computed very easily when not really get into a deep Jacobian math. But in this case, I only just kind of take you through how we can go from this loss gradient and kind of move back up. So this is my loss gradient. I just talked about this earlier. So L, partial derivative of L with respect to Y, that's how everything started. As a practice, let's implement this one more time. Remember how easy it is? It's just a difference of what? Your prediction, which is my Y, or reconstructed signal. Difference between that minus the signal itself. And just go up to like the signal. Prediction minus target. Okay, so this is how it started. All right, and so if I would like to start my backpropagation, so I will move this up to put in this strategic location. Now, so this location is that let's just review that on left hand side is a format that you have seen many times, multi-layer perceptron, and going down here. And this gray area, I circle in gray, is something kind of added supplement into it, so I can perform my backpropagation that was in this way. But if you hide them, it just looks like a forward pass. If you add this back, you can see how the backward propagation work. Okay, so this is going to be right down here, the loss with respect to Y. If I copy over here, but if we set this up, it's kind of cool. It's going to happen. You can see how everything fit together. Remember, let's just going back to my forward pass. In the forward pass, how do we compute this Y? If I remember, the Y is computed by taking the, just say W and B here, taking this, and then we have this H over here and 1 here, right? So if you just multiply them, by the way, it's going to be WH. So this is how we computed earlier. And if we look at just focus on this one, what would be the partial derivative? Let's just ignore B for a little bit. But that could generalize to B because I just want to make it simpler for you to actually understand. So let's say I'm curious about how the loss changes with respect to my H. There's a reason I put it over there. Oh, sorry, now Y. So this term. Okay, let's focus on Y term. So it turns out Y over H, derivative of H is going to be just W. You can see that Y over H is W. If you move H down here, intuitively is W. And similarly, we go back to H. What would be this derivative of Y? Again, this Y over W is H. You can see that they kind of mirror each other, okay? I hope you can get this. So again, Y over, if you move W over here to, you can get this Y over WH. Okay, so this is how this worked out. This is kind of important. Now, in this case, now I can start to backpropagate. What we really care about is how the loss changes. If I change the weight, how does the loss change? So this is going to be, if I write L loss over W weight, it turns out this is as simple as we multiply these two terms, H and this one. Why? Because you look at these two equations over here. Do you see this equation over here? If you multiply these two together, which term got canceled out? Actually, Y got canceled out. Do you see this? Y got canceled out. What do you left with? L over W, okay? So that's how this backward propagation works. It's still maximumfication, but in a different orientation. So that's why we need GPU to multiply matrices forward, backward, all about match modification. So, and then in this case, similarly, let's just look at this way. I have this way. What does this compute? So this turns out this is the loss with respect to the hidden state. Why is that? So there will be, if you multiply these two matrices, what do we get? So these two matrices use a different color. What are we canceling out this time? So this maybe use blue. So it turns out you take attention to these two terms and you multiply, you want to get this one. And which one get canceled out this time? Is again, y get canceled out. And then what do you left with? L and H is exactly what we have here. Okay, so that is the loss. We propagate my gradient with respect to loss over to this location now. Now we can keep moving up. So have this local gradient over here. So that is with respect to the activation function radius. Okay, so suppose, and we have H, and this is a Z, which is before activation. And what would be the difference between the two? So H over Z, suppose we calculate over here. And it turns out this is with radio activation. It's just like when if something is positive, so it looks like this. The gradient, when it was positive, the slope is 1. When it's negative, the slope is 0. Okay? Radius. That's why I'm gonna put another 1 and 0 over here. And then if we move up over here, suppose we want to get the loss with respect to this new Z, what do we need to do? So it turns out we can take this term, and let's use another color. So you can see, let's use purple this time. So if we take this term and this term together and multiply them, the element wise, we're canceling out something this time. We're canceling out H. What do we left with? L and Z. That are exactly what we have here. L and Z over here. So we just propagate one more time to this location. And now remember how Z is computed. Let's move my Z over here so I can just write how it was computed. It was computed by multiplying this weights matrix with my input matrix X over here. Remember earlier we talked about the derivative of Wx and derivative of Wx with respect to Z in this mirroring manner. We can do a lot quicker now. So Z with respect to X is actually W, whereas Z partial derivative of Z respect to W is X. They just flip. And then if we have that set up, then we can calculate the weight gradient for this initial layer. In this case, this one we get. How do we get this one? So we multiply these two. Why is that? Can we prove this? And can actually see when these two terms together, there's something being canceled out. First being canceled out, Z got canceled out. So now you end up with L and W here. Ta-da! And then if you continue this direction, you can continue to calculate this. If you multiply these two, what do we get? We get L over X. Why is that? Again, Z got canceled out. Okay, and there's it's called the kind of upstream gradient and downstream gradient. And why am I not putting actually computing here? Because this is it. This is as far as we want to back propagate to get the loss gradient with respect to the weight in the highest and the initial layer. So there's no more weight I need to calculate. So, but I just write it down here to see you could. If you have more layers above, you just calculate this one and keep propagating following similar pattern. Okay. Hopefully, these are the okay for you to follow through. It turns out if we write in this form, it's very simple math. It's just got canceled out with multiplying back here. But what's interesting is that because I lay out here, it's become easy to implement. So remember, it's all match propagation. Is that for the first one, I just want to copy this weight, my initial gradient. But I cannot just copy this. You have to kind of transpose this in order for the map to shape to match. So I transpose over here. Okay, ta-da. And then everything else is mostly match location. So I'm going to do it very quickly. So metric modification, because upside down, I actually had to select this first and comma and select this weight and got this, okay? And then this going to be this malt, actually, sorry, met malt, met and malt, okay, and malt, and malt. Let's slow down a little bit. Select this one and select and comma, go down and select. Oh, I use mouse. Select this. Okay, so I calculate. What is this again? Show. Oh, so this is loss gradient with respect to weight. That's what we really need because we need that to update the weights. And then we use this transpose. So there's 1 and 0 thing. So I could do is that I could do if my result activation is greater than 0, and then if it's greater than 0, gradient is 1. If not, it's 0. Remember that? The local gradient, kind of think about that. Oh, actually, it doesn't work because I have to transpose to fit the weight, to fit the orientation. Just transpose this, okay? So this one, and then how do we calculate this? We have to multiply two things together. I don't quite remember this. Bring this, show in again. Okay, I want to take this over here and multiply with this. That's my goal. It's okay. So this is going to be move my mouse over here. This times this is element-wise multiplication. Ta-da! So this I have the upstream or the gradient propagated over there. So do you see the numerator is actually a loss? And then now just move again, remind me where I should go. So now I gotta go up. I could go up left, but I don't really need to because I no longer have to propagate above here. So the last metric modification here is this one, med malt, and select this input, and then go down here, select this second matrix and multiply them. Ta-da! So I have this one. Okay. All right, just to convince me this 51 actually works. Actually, sorry, this 18, this transpose. So this tells me that if this is mouse. So this one, 51 corresponds to this one, meaning that if I add a little bit weight, that weight will be multiplied by 51 with respect for the loss. Okay, the loss over here. So let's see whether there's a case. So I'm just going to select a bunch of it so I can hide up to this point so I can see the loss in the same screen. Let's just hide this. Did you see now? I have 83 here. I want to show that if I add a little bit, say 0.1 to the weight, I expect the loss to go up by like 51 times of that. I'm a little bit nervous whether it will work, but I'm just going to do 0.01, see whether 83 becomes 83.51. Something else. Yes, do you see this? I thought it's pretty magical when I got it right the first time. So 83.51. Okay. Whenever I bring the mouse, this back show my ink again. So here, do you see this? Okay, so it's pretty cool. Now I can see, let's go back to 0 and just try a different way if you're not convinced already. So 24. Come on. I need another way to point this. 24 is correspond to this one. So if I add 0.1, 0.01, I get 0.24 to the weight. Will it work? Let's see. 1.01. 83.24 is what I want to see. If I got that, please clap. No, it doesn't. Actually, sorry, I selected the wrong one. It's 43. This is the 43 I want to see. I selected the wrong one. Okay, let's see whether. Okay, sorry, so go back to 1. I see. So 43 is what I'm looking at. Let's keep showing this. Call it 43 is what I'm looking at. So if I do 1.01, I'm gonna get 83.43. Yes, 83.43. Okay, great. I'm quite happy about this. So it shows that this back propagation was calculated correctly because you are able to reproduce. You can able to predict the impact of the change in your parameter weights on the total loss function by that ratio. Okay, so lastly, if I all put it together and through multiple steps, I can actually calculate gradient descent. That's why I have this for over here. So this is a complete calculation of the backpropagation. This is all filled up and it will all work. And then we to the right is the time now. So if I want to do another epoch, so let's just zoom in a little bit, you can see this. So epoch 1, learning rate 0.01. I'm gonna tell you what learning rate is going to be, why that matters. Okay, so this thing. Now what I want to do is that this is one epoch with both forward and backward pass, right? So I have all this space kind of marked out, so make my copy and paste easy. So I'm gonna copy this whole thing. All right, and I'm gonna go back up here and paste this. And it failed. Okay, come on, one more time. Well, maybe I didn't select. Maybe I use my mouse. Going all the way down here and select this block, calculation, computation block, copy. All right, and then I'm gonna move over here to this nice spot and paste. Okay, now I have another epoch. Maybe I can do is that I'm going to go back to 100%, and then I want to this epoch to be 2 increment by 1. So I can do, instead of 1, just say I'm going to do is then here plus 1. Okay, so this is epoch 2. Another thing I want to connect is that is this weight, instead of just a carbon copy of previous step, now actually I have this gradient. This is here. I have this thing I can use now to update my weight. So I'm going to delete all this. And then what I'm going to do is that I'm going to do is this previous weight plus this thing, but it won't work because I need to transpose this. So let's just rewrite this. This weight, previous weight, plus the transpose of this weight I need to update, okay? All right, okay, so this new weight. But that's just, since I haven't really done correctly. One is that we could, this, if we just add that, it's kind of too big. Remember when I do experiment, I used 0.01 to change because this gradient is very close to when you are, it's more like local gradient if you add this too big. So learning rate is a way you can determine, you can define how much step you want to go. So in this case, I actually define my gradient learning rate over here, alpha. This is my alpha. I'll select this one. And then and come back down here to update my equation, but times here. So this is, so you see that from 0 to 0.51 with a learning rate of 0.01. So there's a new weight here. Okay, and 1 become 1.43. Okay, so this is a weight, all right? So just write down the equation is going to be new weight is going to be the previous weight. Maybe use this epoch 2 to 1 plus the loss, this thing I just calculate with my learning rate alpha. So this alpha over here. And what we should expect that, well, actually, I purposely make a mistake here, but I'm not going to tell you what that mistake is because I'm going to go down to my loss and to see that I expected the loss to go down, but I just go from 83 to 577. Why is it going up? Okay. It turns out when you update the weight, instead of this plus, we want to do minus. Why? Because we want to do gradient descent. We want to go in the opposite direction of where the loss increases. The loss increases is a bad thing. We want to go in the opposite direction, which is in decreases. So I have to go update my equation instead of plus. I'm going to make this minus. Okay. So in that case, we're going to see the loss actually goes down. So 83 to 18, which looks not too bad. All right. Okay, so now if I finish one layer, actually this, we can repeat the same process for this way as well. But now we know how to do it. You can watch me. What I'm gonna do is I select my previous weights and biases, and then I add, I'm gonna go up to select my learning rate here, and times, times the transpose version of the weight gradients, the loss gradient with respect to weights I calculated earlier, and then we're going to new weights. Okay, and so now hopefully the loss is still going down, but we're updating weights in 2 layers. Okay, so this is how we can complete the second epoch. So once we have that done, and the rest of it is basically just copy and paste this block that each time we copy this block, because we already this time we actually took care of the relative computation with respect to the previous epoch. So then if I copied this and they're going, because I arranged them in relative location to the previous epoch, so it's just gonna work. So you can see that it's pretty small, but you can see now the loss from 18 to 17 now, from 83 is going down. And I'll just copy one more time here. Copy here. Okay. And then can I see it? What is this? What is my loss now? It's 18. Go back up. Why is that? Anyway, so it's not great. So I'll just take a, if maybe the previously I took too big a step. Now I just copy one more time just for the fun of it. So no, doesn't let me. Okay, one more time to complete this. Take one more epoch and then we'll be able to end today. Okay, go down here. So complete my 4-step, 5-step, 5-epoch. But unfortunately, we did not converge. So the thing they can fix is that maybe you try a different learning rate, that smaller learning rate, or a different learning schedule so it can converge faster. Or maybe this network architecture is not big enough. Maybe the 2 nodes is not enough to really capture everything. Maybe we can add another layer. So in things like that, you can study to add and experiment how you can build autoencoder. Okay, so today that we successfully completed this ambitious plan of going through autoencoder and how to train it by defining a L2 loss function and how we can calculate gradient and how to start the backpropagation process. Pretty messy, but it's still a lot better than seeing this crazy Jacobian kind of 1 xn LO, and then you have the LO 1 over LN, kind of like this. And with a bunch of them kind of stuff is typically in a math textbook, that's what you see. But hopefully this Excel representation is slightly more accessible for you and being able to follow how I trace backpropagation and then go horizontally through time, how you can run gradient descent with the goal of decreasing your total loss until it becomes 0. When it becomes 0, what does it mean in the context autoencoder is that you have perfect reconstruction of your input signal. And if you are able to do that, that is it still kind of means to the end, because your end is that now you also have an encoder that can perfectly capture the code that's underlying your signal. Okay. All right. So that's all I have today. Thank you for listening, and I'll see you soon.